Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. And within this module, we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process. And within the second module, we are currently on the fourth topic, that is process system call API. So as you know, within this topic, we are covering the set of system calls which are related to the process management, right? So within the Unix operating system, we are going over the system call API that Unix offers. And to be specific, we are looking at those system calls which allow us to perform operations on processes. So in the previous video, we have started with the first system call, that is the fork system call, and we have given a basic introduction in the previous video. So in this video, I want to take a more closer look and discuss about some other aspects of the fork system call. So without further ado, let's get started. So let us start the discussion by recalling all that we discussed in the previous video when we introduced the fork system call. So we will quickly recall how the fork system call works. So as you can see in this example, we have process A, and this is the code of process A, and somewhere in the code, somewhere in the function body, there is an invocation to the fork system call. So when this process executes, the control reaches the fork system call, and when we make the fork system call, the control will be immediately passed on to the operating system, right? So that is how a system call works. Whenever you invoke a system call, the control is transitioned to the operating system, and then the operating system will execute a routine or a basically it will execute the system call which is defined inside the code base of the operating system. So as you can see, this is the code for the fork system call within the code of operating system. And when this is executed, what we have is a new process, right? So as you can see, the fork creates a copy of the original process. So the basic function of the fork system call is to create a new process. As you can see, this is the new process, process B. And how does it make a new process? It makes the new process by copying the original process, right? So process B is a copy of process A, right? Everything is copied from process A in order to create process B. So this is how the fork creates a new process, by duplicating the process which invokes the system call, right? And then we also talked about some other points, like there exists a parent child relationship between the original process and the new process. So if you see this diagram, process A is the parent of process B, and the reverse can be also said that process B is the child of process A, right? So there exists a parent child relationship between the calling process or the original process and the newly created process by the fork, right? So now what we are going to look at is the return, how the fork returns, right? So as we have discussed about this, that the fork system call is invoked once, but it returns twice. So as you can see in this diagram, the flow, if you see, the fork system call returns both inside the parent and inside the child also. So we have discussed this in the previous video, why this happens. Let me quickly recall what we discussed. If you look at the parent process, then this return is quite natural, right? So the parent process was executing, it invoked the fork system call, and when the routine is complete, the control is given back to the parent process, and the parent process resumes the execution from the statement which follows the fork system call. So this flow is quite obvious and natural. Let's discuss the interesting one, that is this flow where the fork system call returns in the child process, right? So although the child process did not invoke the fork system call, it was not even existent before the fork system call happened, but the control, or we can say the control, is given back. The fork system call returns in the child process also, right? And it does not start execution from the main, because if we start the execution of the child process from the main, then what will happen is that it will again invoke the fork system call, which will create another process which will start from main, and that new process will again invoke the fork system call, and there will be an infinite chain which will never stop. So this is not the intended behavior. We only want one new process, right? So that is why the control is resumed from the statement that follows the fork in both the parent and the child process. So the child process begins its execution from the statement that is after the fork system call. So this is how the returning of fork works. It returns both inside the parent and the child For the parent, it is like resuming the execution from the statement after fork. For the child, it is like starting execution from the parent from the statement after the fork system call, right? And another thing is about the return values. So we have not talked about this in the previous video, that what is the value that fork returns. So it does not return the same value in both the parent and the child. So this is where the parent and child process start to differ, right? So as you can see, within the parent process, the fork returns the process ID or the PID of the child process that was just created. So for example, let's just assume that the PID or the process ID of process B is 100. So in the process A, that is the parent process, this 100, that is an integer value, and the process ID of process B, that will be returned. Whereas in the case of the child process, a unique value, that is a special value of 0 is returned, right? So as you can see, the fork system call returns twice. Once it returns in the parent, and there the return value is an integer which is equal to the process ID of the child process that has just been created. Whereas in the child process, the value that is returned is a 0, right? This is always the case. This is a rule. So every time in the child process, the value of 0 will be returned. So as you can see, this makes it clear that the child process is not an exact copy of the parent process. There are certain differences between the child and the parent process, although these differences are quite minute and minor. But yes, the child process is not an exact copy of the parent process. First of all, the process ID of both the processes will be different, because as we know, the process ID is a unique identifier that is used to distinguish between all the processes that exist in the computer system. So the process ID or the PID of the parent will be different from that of the child. Also, when the fork system call returns, the return values are also different. In the parent process, it's the PID of the child. In the child process, it's 0. So this return value can be used to distinguish or like find out in which process we are currently in, right? Whether we are in the parent process or we are in the child process. We'll soon see an example how this return value is useful, right? So this was about the return values. Then let's see what happens when the fork system call fails. In that case, how does it work and what is the value that is returned? So let's assume that the parent process, the process A, invokes the fork system call, but for some reason the fork system call failed, right? And if this fails, then obviously no new child process will be created, right? That is, the operation has failed, and the value that is returned to the parent process is -1. So this -1 indicates that an error has occurred and we could not, the operating system could not create a child process. Whereas in the case that the fork is successful, right, the invocation of the fork system call is successful and a new process was successfully created, then as we discussed, in that case, the value that is returned to the parent process is the PID of the child process, right? So this was about the return values of the fork system call. And now what we will do, we'll see an example where we'll see how the values, the different return values that are returned to the parent and the child process can be used in our code, like to distinguish between in which process we are currently executing, right? So let's see this example. So let us see this example code. Here, as you can see, this is a piece of code written in C. Let's understand the statements that are part of this code. So as you can see, the first statement is we initialize the integer variable x with the value of 1. So x is equals to 1. Then we have the invocation to the fork system call, and we are storing the return value from the fork system call into this integer variable ret, right? Then there is a if else statement where we are checking the value of ret. If the value of ret is 0, then basically it means that we are currently executing in the child process, because if you remember, we had talked about this, that the fork system call returns twice, and once in the parent where it returns the value of the process ID of the child, and in the child process it returns the value of 0. So if the ret value is 0, then we are in the child process and we do some set of operations. Basically, we decrement the value of x, so 1 will become 0. And then we have a printf statement where we print the process ID of the child, the return value in the child process, and the value of x in the child process. Similarly, if it's if the return value is non-zero, right, which means that it is basically the process ID of the child process, right, which is being returned in the parent process. So in the parent process, the else part will be executed. Here we are incrementing the variable x, and that again we are printing the process ID of the parent process, the return value in the parent, and the value of x, which should be 2, because 1 will become 2 in the parent process. So let us see the output of this piece of code. So when we execute this piece of code, we have some kind of output like this. So let's say this is the parent process, its process ID 774. The child process, the parent ID is 775. In the parent process, the value of return is equal to the child process ID, that is 775. And the return value in child process is 0. So this is the printf. This is basically the result that we get after executing this piece of code. So let's also go over the execution line by line and see why this kind of output is there. Although we already discussed, but let's understand line by line. That will give us much more clarity, right? So we start execution and the value of x is 1. Then we fork, basically invoke the fork statement. And once this is done, we'll have two processes, right? As you can see, we'll have two processes. In the parent process, the fork returns the PID of the child process, which is 775. In the child process, it returns 0. Then we check the, basically we compare the return value with 0. Here, in the first case, the execution will go to the else part. In the second case, the execution will go to the if part. So this is how the execution proceeds. In the parent process, we increment the value of x. So 1 becomes 2. So you can see within the parent, the output is 2. The process ID of parent is 774, return value 775, which is equal to the process ID of the child, and the value of x after incrementing 1 becomes 2. Right, in the same way, in the child process, we decrement 1. So that is why the value of x is 0. Process ID is 775, return value is 0. So this is how basically we can use the return value of the fork to basically perform different things in the parent and the child. We do not want always want to perform the same thing as the parent, right? Because if that is the case, then we'll after executing fork, we'll not be able to do any new work, right? We create a new process because we want to do some kind of new work, right? So that is why having this distinction, a way of distinction via the return value, you can check the return value, and depending on the return value in parent, you can do different tasks, and in the child process, you can do different tasks. So this is how the fork system call works, and its return value can be used to perform different tasks in the parent and the child process. So if you carefully look at this picture, this output, you can see comparing the output of the parent and the child process, the process ID of the parent is different from that of child. So 774 and 775, right? Similarly, the return value of the fork system call in parent and child is different. 775 in parent, 0 in the child. So as you can see, this slide basically kind of portrays the differences between the parent and the child process. Although the fork system call, when it is creating a new process, it duplicates the parent process, and almost everything is a copy of the parent process. There are some things, some minor things which are different between the parent and the child process. So as you can see, some of those is, first of all, the process ID. Obviously it should be unique because each process should have a unique identifier, right? So that the operating system can distinguish between the parent and the child. Similarly, the return value should be different so that the user, while writing the program, can write program in such a way that they might want to perform one kind of operation in the parent and another kind of operation in the child. So this was about the differences that exist between the parent and the child process. We'll look at one more difference, right? So the point that I want to make is that the child process is not an exact copy of the parent process, and we are just looking at some of the differences that exist between the parent and the child. So if you see, this is a process A, this is the process control block of process A, and this is the address space. So when the fork system call executes, it will create a copy. So when by creating a copy, we mean it will copy the process control block of process A, and that is how these two will be duplicates of each other. Similarly, the address space will be exactly the same, right? The few differences that we just talked about are the process ID, the return value, right? One more difference that exists is that basically every process, right, it has a parent process. So if you see, the information about the parent process is also part of the process control block, and this is the process control block from the XB6 operating system, right? As we know, the process control block is used to represent a process. It contains all of the pieces of information that is required to represent a process. So in the XB6 operating system, there are two fields that I want you to pay attention to. One is the process ID, right? So this is unique for every process. And then there is a pointer to the parent process, pointer to the process control block of the parent process. So as you can see, this is a struct proc, and proc is the type of this process control block. And in every process control block, there is a pointer to the parent process's process control block, right? So the point is that every process has a parent, right? Except for the first process, the init process, that is a special process created by the operating system. Apart from that, every process has a parent, and the information about the parent is also part of the process control block. So this field will also be different in when we create a new process via the fork system call. This field will also be different in the parent and the child process, and you can understand why, right? So for example, if process A invokes the fork system call and creates process B, so let's say these are the process control blocks of A and B. In process A, let's say the process ID is 200, and let's assume that the process ID of the new process, that is process B, is 300, right? So, and this ppid, that is the parent process id, right? So these pieces of information is also part of the process control block. So what will be the values here? So for B, we know that the parent is A, right? So the parent process id will be the same as the process id of A, which is 200. So 200 is the pid of process A, and that is what we will store in the ppid, that is parent process id for process B. And let's just assume that the parent process of A has a process ID of 100. We're just assuming a random number. So you can see these two values are different. The process ID of process A and process B is different. And so it's true for the parent process ID, right? We could also store the pointer to the PCB, but I'm just storing the parent process ID here, right? So this is again another field which is different between the process, the child process, and the parent process. Again, the point that I want to make here is that the child process is not an exact copy of the parent process. There are certain fields, certain pieces of information that are different between the parent and the child process. So there are three things we already know. One is the process ID. Second, we just studied, is that the parent process ID, and third is the return value. So these three fields, at least these three fields, are different between the parent and the child process, right? And to illustrate this fact, I have a very simple small example. This is a piece of code again written in the C language. Here, if you see, first of all, we at the very beginning of the main function, we invoke the fork system call, and we store the return value in the integer variable x. And here is an if else statement. So we check the value, the return value. If it is 0, then we print the we execute in the child process. If it is non-zero, we execute in the parent process. And all we are doing is just printing the process ID and the parent process ID in each process. So to get the process ID, we already know that the system call that exists in Unix based operating system is getPID. And similarly, there is another system call called getPPID. As you can understand, this is the system call to get the information about the parent process ID. PPID is parent process ID, right? So when we execute this piece of code, this is the output. So you can see the parent process ID in this case, in the example that I have run, this is the output. The parent process ID is 1927, and the parent process ID of, so basically in the parent process, the process ID is 1927, and the parent of the parent process has an ID of 140, right? And in the child process that is created after the fork, the process ID is 1928, right? And the parent process ID is 1927, right? So this is how you can see, the first of all, the process IDs of parent and child is different, and so is the parent process ID, right? So this was another example. We saw how there are certain pieces of information which are different in the child and the parent process. So now we have been discussing about this fact that there exists a child parent-child relationship between the calling process and the new process that is created after fork, right? So in this example, if you see, process A invokes fork and process B is created. So we have already talked about this, that process A is parent of process B and vice versa, process B is child of process A. So there exists a parent-child process relationship between the calling process, the original process, and the new process that is being created. So eventually what happens is that as the execution proceeds, eventually in the operating system we have a tree, or we can say a hierarchy of processes, right? Each process creates a new process, then that process might spawn new processes. So in this way we have a hierarchy structure, right? And all the processes are related with each other in the form of a tree structure. So this is an example of how a process tree might look like in the Unix based operating system, right? You can see the first process that is created is system D, that is a system daemon. It is launched by the operating system. It has a process ID of 1, right? Then this system daemon launches further processes. This red like The border in red indicates that this is launched by the operating system. This is a system process, right? And the others are basically user processes. So here it is just an hypothetical example. You can see the initial process launches the login daemon, which is basically used to authenticate the user. Whenever you boot up the system, the first screen that is presented to you is this login daemon, right? And after you log in, you are presented with the bash, where you can enter more commands into the terminal, right? Let's say you enter the ps command or the vim command. These are the different utilities or commands that are present on the Unix based operating systems, which you enter on the bash terminal, right? And then again, it is a hypothetical example. The system D, the initial process, would launch other daemons also, which are useful for the functioning of the computer system, right? So this is a process tree, and if you want to find out the process tree in your system, then there exists a ps command, and that will give you the information about all the processes that exist on Unix based operating system. So let's do a quick demo of the ps tool in Unix based operating system. We'll see how using the ps tool we can get information about the different processes in the Unix based OS. So now we will quickly go over the ps command, which is used to get the information about all the processes in the Unix based operating system. So I will list out the like all the processes in Unix. So the command that you can use is ps, and if you give this set of commands, that is -e, f, l, and minus forest, then this will give you the complete list of processes on the that are running on the current operating system, right? So basically, let me explain quickly the set of flags that I have used. So -e flag is used to select all the processes, right? Basically, we do not want to leave out any process from this list that we are printing. Then this f is used to like print the name of the process in full format, that is the full name of the process, and also print columns like ppid. If you do not use the f flag, then a lot of columns will not be printed here. Again, l is also used to print like more information, right? The more information you want. So this is like a full listing that you want to see. So f and l are like qualifiers that are used to print more information, more detailed information, right? And this forest is used to like display the processes in the like process tree, right? The hierarchical structure that we just talked about. So the very first process will be the init process, which has a process id of 1, that will be printed at the top, and then we will have the other processes printed as the hierarchy proceeds, right? So this output that you see is a very limited one, because I'm not running it on a full-fledged Linux, right? I do not have Linux installed in my system. I'm running on Windows subsystem for Linux. Basically, within the Windows operating system, this is a container, and within the container, you can see this output. So that is again another useful tip, that you can run one operating system inside another, right? So if you look at the columns that we have here, I will not go into the details of all. First is like the user ID, right? Which user is launching this process? One is the root user. The other is the normal user, that is with less privileges. Here in this case, this is my alias, that is Phoenix. Then for each process, the process ID is printed, and then parent process ID is also printed, right? And apart from them, that the size, the memory that is being consumed by each process is also being printed, right? Then the time at which they were launched, all of this, and finally the full command, right? Not just the process, the full command. So this is the shell, this is the ps command, right? So you can see all of these processes that are currently on the on this container that is running on Windows. So this is a Linux container that is running on Windows. So this is how you can use the ps command. And as we discussed in the previous video, if you want to know more information about any command on the Unix based operating system, then you can use the man command, which will print out the manual pages. So this is the documentation for ps, like report a snapshot of the current processes, and you can see different flags and how to use them have been listed out properly here, right? So this was a brief introduction to the ps command that you can use to see the information about all the processes that are currently running on your computer system. So let's come back to the slides, and here what you see, this is an output from a real operating system. I mean, that is Linux that is installed on the actual computer system, not on as running as a container on Windows, right? So this is from a full-fledged operating system, and as you can see here, there are way more number of processes that are there compared to the one that we just saw, where it was just some processes running inside a container, right? So it's the same command I have used, the ps, efl, and forest, right? Again, there is another command called pstree. PS3 prints just the name of the processes, and as you can see, it prints them in a hierarchical fashion, right? So this is the tree-based structure that you can see when as output when you use this PS3 command. So this is another useful command that you can use if you want to see the process tree. And this was about how you can get the information on Linux. If you want to see the same kind of information on Windows, then there is the task manager, right? Windows also displays this information again in a more visual way. The interface of the Windows operating system is more interactive and more colorful. So here again, the name of the process, process ID, status, the username, resource consumption like CPU, memory, right? And the description of the process. So task manager, if you visit on the Windows operating system, within the processes tab, you can like get the information about all the processes that are there on your system. So guys, this was it that I had to cover in this video. We talked about the fork system call in more detail. We talked about how the return value of the fork works, right? We discussed that within the parent and the child process, we have different return values, right? And we also saw what are the values that are different between the parent and the child process. In the parent process, basically the parent process ID, the process ID, and the return values are different between the parent and the child. And then we eventually talked about the fact that as we create more processes in the computer system, there eventually is a process tree, right? Since there is a parent child relationship between the processes that are created using fork, so we have a process tree. And if we want to see the information about all those processes, then we can use commands like ps3 on the Windows operating system, sorry, Unix based operating systems. On Windows we have the task manager, right? So this was it for this video. So guys, thank you very much for watching. I will see you in the next video. Thank you.